Good day, everyone, and welcome. My name is Rena Kalloo, and I will be giving a brief update on one of the projects at Cook Research Center. So the activities presented here are part of a larger project, the MOCCA Project. MOCCA is the acronym for Maximizing Opportunities in Coffee and Cacao in the Americas, funded by USDA FAS as part of the Food for Progress program and executed by TechnoServe and the Lutheran World Relief. So the sub-project, this aspect of it, focuses on rehabilitation and renovation of the International Cocoa Genebank, Trinidad, with the specific objective to improve the conservation status of the International Cocoa Genebank and management system. So we conducted a gap analysis through the gene bank and the capacity of Cocoa Research Center, and we came up with a few threats and some activities that would be able to address these threats. So the first one was the low tree number per accession. So trees within plots would have died through a variety of reasons, debilitated by pests and diseases or identified as not true to type. What we did, we decided to conduct a survey to identify all at-risk accessions, collect budwood and grass for safekeeping in the greenhouse, improve the health of the trees by sanitary pruning and fertilization, and propagate these at-risk accessions for infilling into the vacant plots later on. So the outcome of this would be that all accession plots would have at least 5 healthy trees. Second area we identified was the lack of capacity for propagation. So we were not able to replace all the lost trees at the required rate due to the inadequate propagation facilities. So we set about to establish a propagation greenhouse, which would improve the capacity to infill the vacancies within plots. Third area was the non-homogeneity of the accession plots. So within accession plots, there's a percentage of mislabeled trees, some as high as 25%. So in order to have a completely homogeneous accession plot, we set out to DNA fingerprint the trees within each plot. We also identified a lack of a duplicated strategic collection. So we identified trees that would go into the strategic collection to be duplicated, DNA fingerprinted, and started to propagate these accessions for duplication. Fifth area was the lack of a database for research and gene bank management. What we want is to have an access to update information to guide gene bank management decisions and utilization. We established a tree and plot barcoding system and a georeference database that will be able to guide conservationists and researchers. So International Cocoa Genebank is almost 40 years old. It covers about 30 hectares or almost 100 acres of landscape. The accessions were planted as clonal trees and plots of either 4, 8, or 16 trees. So initially we started off with 16 trees, but to maximize space, we propagated accessions with 8 trees. The 4 trees are those nursery plots within the collection. And the gene bank consists of about 2,300 accessions produced. Every year we do a survey on the trees and accessions in the gene bank, and we identified 800 at-risk accessions. At-risk accessions are those with 1 or 2 trees within the accession, which means that they are vulnerable to genetic erosion. So after we identify these trees, we tag them and subject them to cleaning, structural and phytosanitary pruning, pesticide application where necessary, and fertilization. This was to improve the overall health of the plant and encourage flushing for healthy vegetative growth in order to get the ideal stage of shoots for propagation. What we also did was immediate propagation of a single copy accession. So these were actually grafted onto rootstock and kept in the greenhouse for safekeeping. So a total of 115 accessions were propagated via grafting, and about 94 of them we have surviving thus far. This is just a visual representation of the trees that were tagged in the greenhouse, in the gene bank, sorry. They were tagged with flagging tape to easily identify. And the photo to the right shows the nice flushing of the trees after they were subjected to pruning and fertilizer application. So we're moving on to the propagation facility. What we did, we took one of our existing greenhouse structures. It measured 50 feet by 50 feet before spacing. And what we did, we built and repurposed it into a propagation house, a hardening facility with a mixing system. The previous structure was about 6 feet tall. Rita, the young lady there is used for height reference. So that height was not very ergonomic for persons and ideal for the plants within the greenhouse. Also in the bottom right photo, the plants are actually placed on the ground, which is also not ideal for walking or access space. What we did, we applied structural changes to the height of the greenhouse, the flooring, and the internal infrastructure. And this was our end result. So we had an increased height to reduce heat buildup, had a split roof design to dissipate the heat, put plastic sheeting at the top to improve light, and a removable 33% shade to regulate the shade within the greenhouse. And there was also 33% shade on the sides to improve the light. We increased the water capacity with 2,000-gallon water tanks. We introduced a hardening facility with 20% shade and no plastic sheeting on that area, just 20% saran netting, and that was able to accommodate 800 plants at a time. We reconstructed the floor and installed 20 propagation tables. So the two images to the right-hand side would show the frames of the tables. Those were actually covered in aluminum sheeting to accommodate potting plants, potted bags with the plants, sorry. And these were able to accommodate 1,632 plants. Those benches actually measure 16 feet by 4 feet. The final stage is to implement the automatic misting system. So with the restrictions that we have now, that system has been a little bit delayed, but within coming weeks, we hope that it will be completed. So we did some propagation of the at-risk accessions and strategic collection. So just to say what the strategic collection includes, it's a representation of the phenotypic and genetic diversity covering the 10 genetic groups, also includes the trinitarian and refractario genetic groups. Also represented in this strategic collection is the variation in bioaccumulation of cadmium. So we came up with 500 accessions for the strategic collection, propagated by rooted cutting. Why rooted cutting? Simply to eliminate the rootstock effect. Selected disease-free semi-hardwood shoots. So semi-hardwood shoots are those that are light brown, that still have some green on the underside. And in experience, it is usually 2 weeks after a flushing period, we get this ideal stage of budding. For anyone that has propagated via rooted cutting, they would know that there's a spectrum of success with rooted cutting. So they're easy to root and difficult to root successfully. In order to reduce the tonal difference for ease of rooting, we optimize the method for better rooting success. We used cocoa peat rooting media that was able to hold moisture but had ample drainage for the bulb. And we optimize the rooting hormone concentration of 4 grams per liter, IDA to NA in a 3:1 ratio. So IDA is indole 3-butyric acid, NA is naphthalene acetic acid, and both of these are synthetic oxygen rooting hormones, and they act as a root stimulant. And we also, together with this rooting hormone mixture, we applied a 3% sucrose solution. Since the difference in tonal rooting is mainly nutritional. So these were actually propagated in the existing infrastructure that we had while we waited for the greenhouse to be refurbished. So the two photos at the bottom show plants in the propagation bin and when they were undergoing the hardening stage. So for the fidelity testing, to be able to have a completely homogeneous accession plot. We did identity analysis for 622 accessions, and accessory background of 723 samples was determined. So Lambert is going to expand on this aspect of the project during his presentation. So that's what I'm going to say about that area of the fidelity testing. So we move on to the GIS mapping and the database development. So the GIS, which is the Geographic Information Systems, that will facilitate the location of the trees and the accessions and the plots within the GenBank. And the database is going to allow for the retrieval of tree and accession linked information. So this is just a Google snapshot of the International Cocoa Genebank, so we'll know what we're working with moving forward from here. So for the database development, that's just the architecture to the left just shows how each area is interconnected and what is used to be able to populate the information in the database. So the API is just Data Application Programming Interface. WMTS is Web Map Tile Table. So when someone clicks on the database, that is the landing page to the right-hand side, and it consists of two interconnected record points. So the first is the accession plot database that would identify every accession and all the related information that comes along with it. And the second pair is the tree database that would identify every tree in the collection with the range of data fields regarding that tree. So how is this data collected? So we use a GNSS RTK surveying technique. So GNSS is Global Navigation Satellite Systems, RTK, real-time kinematics. This was the method employed in the field to select the locations of trees, accession, plots, all that. So it consists of a base station and a roving operator, which is the image to the far left. The satellite receiver on a pole, which is the image to the far right. And this is some of the information that was collected. So we were able to collect cocoa tree locations and accession plot locations. So to date, we have mapped about 1,300 plots, accession plots, and approximately 4,800 trees. We also mapped the shade trees and the infrastructural assets within the GenBank. So the infrastructural assets, the hydrants and the bridges. The hydrants are part of the irrigation system of the GenBank. So we mapped 45 hydrants, 29 bridges, and the shade trees, we mapped 114 shade trees and 76 boundary trees. So these data points will be used to establish the barcoding system that will be linked to the searchable database. And as of now, the digital GIS map is approximately 50% complete. Next, we used remotely sensed LiDAR data to collect these images. So we derived contour map, digital elevation model, and a drainage layout. So LiDAR is light detecting and ranging. And that is just where imagery is taken from a plane that uses these specialized sensors, and they emit light pulses to the ground and then retrieve the signal to determine the height and location of the objects on the surface of the globe. What I will do is just have a short 40-second video that will show how the data was generated. So it's a three-dimensional simulation that provided us with the capability to extract useful information and gain a better understanding of the environmental interactions. So together with this simulation, we would also incorporate additional remote sensing data from both the drone and satellite imagery. So, for example, we can collect plant health and heat stress indicators from the remotely sensed data. So all this shows how we are implementing the precision agricultural technique at the GenBank. So how do we bring this all together? So even though we experienced some delays due to the restrictions, we're currently actually in a restriction period right now, we have made considerable progress with the status and the investment needed to renovate the collection. We've been able to improve the fidelity within the collection. We've improved the overall health of the collection, and we've started to duplicate the collection. better support the utilization of the collection for breeders. We've also established a functioning database that will help with conservation activities as well as research activities. And our immediate goal now is to continue and complete the interventions we've made thus far with a 6-month no-cost extension to the project. So this project, we just would like to acknowledge the government of the Republic of Trinidad and Tobago, Cocoa Research Association of the UK and its contributors, the ICE Cocoa Futures Europe, Mondelez, Mars Wrigley, Barry Calvo, Olam, Cargill, Zitad, and Whittaker, who all contribute to the long-term conservation of the collection, and specifically the MOCCA Project through the USDA and FAS, through the Food Progress Program, for specifically funding this particular aspect of the project. So we thank you.